So hello everyone, this is the second talk I'm giving today. And last year, Dr. Wegland and I present a method to, present a method to remove the ground roll and the ghosts, and meanwhile retain the energy of the reflection data. So this year we continue that study to provide an effective solution with a significantly reduced data requirement, and that requirement is available for the current leading edge onshore acquisition. And later in a minute I will tell what the last data requirement is. And this talk is sitting on the top part of this onshore processing tree, and the objective here is to obtain the reflection data without ghosts, without ground roll, in preparation for the subsequent processing. So among the advance and progress of this year, this talk is looking to reduce the data requirement for onshore wave separation. Now, before looking at what we are doing here, I'd like to remind you the contribution made to reduce the data requirement in marine. To some extent, that can be the analog of what we are doing here. In 1990, Wegland and Seacrest provide a theory to separate the reference wave and the scattered wave. And this formula shows you how to predict the reference wave. As this figure below shows, the reference wave is the wave that starting from the source and ending at the field, it does not experience the Earth. So oppositely, the scatter wave is the wave that does experience the Earth. Now, to predict either the reference wave or the scatter wave, you need to have both Green's function G0 and its normal derivative in the reference medium, which is acoustic here. And besides, you need to measure both the pressure field P and its normal derivative along the receiver cables. And so in those days of 1990s, people do not have the normal derivative. So the scientists independently in BP, Shell, and Statoil provide the theory of wave separation without needing the normal derivative. That requires the Green's function G0 to be vanished along the acquisition surface to get rid of the requirement of the normal derivative of P. So that strategy allows a less demanding acquisition. Today, that contribution is less significant because the marine acquisition has advanced. People have a gel streamer, have over-under cable, which can provide the normal derivative information effectively. But moving to land, there is a similar issue there. Today is rarely having the analogous land data of normal derivative that express itself as attraction. So this formula is used for onshore wave separation, and it provides a solution to separate the ground roll and ghost out from your reflection data. As the output U up here is the outgoing displacement reflection without ground roll and ghosts. Please notice that this is not a filtering method for ground roll removal. This is a wave theory-based method to predict the outgoing reflection data, thereby there's no damage here. And to obtain this effectiveness, we need to have Green's function G0 and the stress tensor of Green's function. Different to marine here, the reference medium is elastic, so both Green's function and its stress tensor are more complicated. They are higher order tensors here. And besides that, you need to measure both the displacement U and the traction along the acquisition surface. Both of them are multi-component. So you can see in comparison with marine, the land has a higher level bar of data acquisition. Now, people usually measure the displacement, so what about the traction? What is that and how to obtain that? Next, I'd like to use a simple picture to remind you of the fundamental definition of traction. Imagine you have an internal surface S inside this continuous medium, and the normal vector is n here. So the traction can be defined at this point by considering an infinitesimal force delta F acting across an infinitesimal area delta S along the surface and taking the limit of delta F over delta S as delta S approaches 0. So from this fundamental definition, you can see the traction actually quantifies a contact force with which the particles from one side of the surface act upon the particles of the other side. The traction actually can be computed with the Hooke's law as shown in this slide. It's very complicated, so I'd like to remind you with the basic idea. And X and Y and Z here are those three components of that normal unit vector. And lambda mu here are the lamb parameters. So in order to compute the traction at that specific point, you need to have the local property of the Earth. And besides that, you have these terms. They are the derivatives of displacement along different directions. Now we back to the algorithm. You can see in order to compute the traction along the acquisition surface, you need to have both the local property information and the derivative of displacement along different directions along that acquisition surface. Well, in this talk, we will assume the local property in the vicinity of the measurement surface is known. So here we have give you the framework showing what's required in principle. The natural question now is what will happen if you satisfy the data requirement? Say you have both the multi-component U and the multi-component attraction along the acquisition surface everywhere. How does it perform? Next, I'd like to use one example from last year's annual meeting to remind you the performance of this method, given everything is needed. The method can be applied to both on-surface receivers and buried receivers. For this example, the receiver is at 100 meters beneath the surface. And here we only show you the result of the horizontal displacement. But to obtain the outgoing UX or outgoing UZ, both the multi-component displacement and the multi-component attraction are required as input. So for an easy connection, I'll only show you the total UX here as one part of the input. For this data, you have the direct wave, you have the relay wave, and you have primary, you have these ghosts. Now with the data with all these different events, you put that into that algorithm, you will have this prediction. Only primary are left in your output result. Flip back and forth, you can see originally the interference among these different events are very serious. But given this, the method can effectively predict the primary without damage. So with this example, you can have confidence that when you satisfy the data requirement, the method can effectively separate the ground roll and the ghosts out from the data and without damaging the reflection data. Again, this is a straight wave prediction using the wave theory, and that is not a filtering method, and there is no injury here. So you may have a question that whether this method still works if you do not satisfy the data requirement, which is usually true for the real acquisition. For example, you may do not have the derivative of displacement to compute the traction everywhere along the acquisition surface. So can this method still be useful? We are not looking for perfection. We are looking for, can we be useful? Can we be effective? So from this perspective, I'd like to show you the latest work we are doing to reduce the requirement of traction. This work is responding to the limited onshore acquisition. Here, I'd like to use a 2D case to show you how do we achieve that traction requirement reduction. And this method is applied to 3D case also. This is a land experiment. You have an air half space. You have the Earth layers with heterogeneity marked with different colors. And the source is a force vector acting on the air-Earth boundary like the Weber size. And the receivers highlighted by these green triangles are slightly below the air-Earth boundary, and it measures the Earth particles vibration along different directions in form of a multi-component displacement. So next, I'm going to show you some approximation we make, and later you will see with that approximation, the data requirement of the theory can be significantly reduced. The first thing is we use a vacuum half space to approximate that air half space. Thereby now you have the vacuum Earth model here, and besides, we assume this external force is local, and it can be expressed as a time function by a spatial delta function. And f of t can also be called as the source wavelet. So this is a very reasonable approximation, because when you use the vibroseismic track to produce the force energy, it's very local in comparison with the whole exploration regions. Now, since the receivers are right beneath the boundary, then the boundary condition says that along the acquisition surface, the traction equals to the minus f by a spatial delta function. Here we express that in the frequency domain, then we can directly substitute this formula into the original algorithm we showed earlier. And there are two separate integrals here, and it is performed in the space frequency domain. We input this spatial delta function into the second integral. You will see that the second one turns out to be a product between the force and a Green's function that is starting from the output point and ending at the source point. This one has an analytic form. So comparing with this original formula and the simplified one, we call this a simplified one. You can see that instead of requiring the traction everywhere along the acquisition surface, we only need to have the force information at the source point or approximate source wavelet to finish the computation of the second integral. That's what we do here. And now we can see with the vacuum Earth approximation, the data requirement for the wave separation is significantly reduced. What you need is a multi-component displacement U and an approximate source wavelet F. And the multi-component displacement U is available for the current leading edge onshore acquisition, and the source wavelet can be approximately estimated with the base plate vibroseis. So the most important thing here is there's no need for the traction anymore. And the next question is, can this assumption make some useful result? What does it mean? It means that if you generate data from the actual air over Earth and substitute the data into that simplified algorithm with the displacement U and the source wavelet, and process the data as though it was in a vacuum Earth world. So can this produce some useful result? If yes, then this approximation will make the current leading edge onshore acquisition to benefit from the theory to remove ground roll and ghosts. And it is practical valuable. So next, I'm gonna evaluate this approximation by using the wave showing this red box. And this is a model we are using here. And it's very simple, air half space and a two-layered Earth. The source is a vertical force for simplicity and is acting on the air's boundary. The receivers is right below the air's boundary. It measures the multi-component displacement. So here the f of z is, that information is assumed known here, and it is actually a time function. We substituted this f of z to that simplified algorithm together with this multi-component displacement, see how it performs. So if that algorithm can effectively separate the ground roll and the ghost out from the data, the left portion will be the outgoing reflection data, or the primaries. And besides that, we locate the output point R on the acquisition surface. So if you effectively predict that primary, that should be exact portion of your input data. And we only show you the Z component result here. Given this model, you have this total UZ here, and it's generated in the air-Earth model. So looking at this, you have this relay wave, which has a strong amplitude, and you have these primaries. So each parameters here are interfered with the ghosts, since the receivers are right beneath the air-Earth boundary. So the outgoing primary and its corresponding ghosts have the same travel time here. And you may see there are 3 events here. That's because this is the elastic wave field, and you can have different wave component. It can be P wave, or can be S wave, or even the converted wave here. Now we put this data into that simplified algorithm that assumes the data is generated in the vacuum Earth, which is not true. You will have this predicted result shown in this slide. So now flip back and forth. You can see this is the total wave, this is the prediction result. So the majority energy of the relay wave has been removed in your output result. There is a residue here, but its energy is very weak. And if we look at these 3 events in the total wave, you can see all these 3 events have both primary and ghosts. Out prediction, their amplitude is altered because the ghosts are not exist in your output result. Now, to further evaluate the accuracy of this predicted primary, I like to compare this with the primary generated with their analytical forms, given the model is very simple here, as shown in this slide. So each primary can be generated analytically, thereby it provides the ground truth result. Now, if we compare this most accurate result with the predicted result from this simplified wave separation algorithm, you can see the amplitude match very well. So what does it mean? It means that this method has effectively separated the ghosts out from the data, and there is no damage of your primary data. And one single trace plot can provide us more detailed information. And this black line here is the total wave at offset 160 meters. And you can see this is the relay wave. It has a particular significant amplitude, and it even goes out to the plot limit here. And these 3 events are the PP wave, PS or SP wave, and the SS wave. So all these 3 events here are interfered by the ghosts. Then the blue line here shows you the accurate primary generated with the analytical form. You can see that there's no relay wave here. And the difference from between the black line and the blue line in these events are because there is no ghost in your primary. And so later I will show you the predicted primary. If that prediction result is closer to this blue line, it's closer to accuracy. Okay, so this is the result, the predicted primaries with the simplified wave separation algorithm assuming a vacuum Earth. So you can see almost everything is here, and except a very small residue here. So from this result, we can see with the assumption that the data is generated in the vacuum Earth, which is not true because the input data here is actually generated in the air-Earth model. Even though the simplified algorithm can still produce the acceptable and reasonable result, and most importantly, you don't need the traction anymore. Okay, so let's drop the conclusion that. Here we have shown you what have been done before. Say, assume the traction requirement is satisfied, then the method is able to effectively separate the ground rule and the ghost from your reflection data, and without damaging the reflection data. And we understand that the traction requirement is not easily to be satisfied everywhere. So this year we make an approximation that the air-Earth model is actually the vacuum Earth, and with that assumption, we get a simplified algorithm. From the previous numerical test, we take the data from the air-Earth and substitute that into this simplified algorithm and process that as if it was in a vacuum Earth world, and it can produce acceptable and useful result. So Currently, in general today, that onshore acquisition cannot benefit from from this original theory. What we are showing here is a significantly reduced data requirement. It replaced the requirement of traction to be a simple source wavelet, and it can still provide effective result. So it provides a positive opportunity for ground roll removal with the current leading edge onshore acquisition. Thank you.